Good day, wonderful students. You're welcome to today's lecture on mathematics. We are here to discuss about a new topic which actually discusses about what? About geometric progression. Geometric what? Progression. We have already known from our elementary studies about what is meant by a geometric progression. That's GP. When a sequence is said to be in geometric progression. Remember in our last episode, we said that there are two types of sequences. A sequence can be in arithmetic progression, or it can be in what? In geometric what? Progression. Now, sequences in arithmetic progression are sometimes called linear sequences. But sequences in geometric progression could sometimes be called what? Could be called exponential what? Sequences. So we can call it geometric sequences or what? Or exponential sequences. Exponential what? Sequences. Exponential sequences. Geometric progression or exponential sequence. But the issue is that if I am given a sequence, how am I able to identify that that sequence given to me is in geometric progression? It is already known from the elementary knowledge that a sequence is said to be in geometric progression when there exists a common ratio between any two consecutive terms of the sequence. I repeat, a sequence is said to be in geometric progression when there exists a common what? Ratio between any two consecutive terms of the what? Of the sequence. That is the complete definition of a sequence in geometric progression or exponential what? Sequences. But we are not here to dwell much on the issue of exponential sequences or geometric progressions. But nevertheless, I would like to give you an example to refresh your memory about this. Now, if you look at the sequence, let's look at the sequence 2, 4, 8, 16, and so on. 16, 32, okay, let's just stop there. Now, this sequence contains 5 terms. You observe that there is a relationship between the consecutive terms of the sequence. When I talk about consecutive terms, I mean maybe the first term and the second term, or second term and third term, or, third and fourth, or fourth and what? Fifth. Consecutive, pairing. One after the what? Other. As in, after this, the next. Okay? So, if you look at the consecutive terms of the sequence, if it happens that there is something relating the consecutive terms of the sequence, such that this relationship is modeled in the fact that they have the same what? Ratio. The same what? Ratio. So, if you look at this now, the ratio between 4 and 2 is 4 over 2. Here it gives 4 over 2, and 4 over 2 will give us what? Will give us 2. Look at between the second term and the third term. You can see that we can compare these two terms by using ratio or division. And that means now 8 over 4 by comparison gives us what? 2. In the same vein, let's call it R, common ratio. In the same vein, 8 and 16 can be compared. And by comparison, we can compare them using division. You see that 16 over 8 gives us what? Gives us 2. The same thing happens here. We also have 2 here between this guy and this guy. So you can see that the ratios between two consecutive terms happens to be the same all throughout the sequence. So therefore, whenever such happens this way, whereby you can see the existence of a common ratio among two consecutive terms of the sequence, we then conclude that the sequence is said to be in what? Geometric what? Progression. So this is a typical example of a sequence in geometric progression. Then also, as a revision, we have also seen that the terms of a sequence, the missing terms, the missing terms of a sequence in geometric progression can be found. For example, assuming I don't know that 4 is existing in this particular point. Maybe I call this is x, is unknown. This term is unknown, x. All right? But I'm not saying that. It is possible that if it happens that we know or we are aware that this sequence is in geometric progression, then this missing term can be found only when the value of the common ratio and the value of the first term is what? Given. So if you are given the first term and the common ratio, you can find the missing terms of a sequence in geometric progression. Please don't confuse yourself between geometric progressions and arithmetic progressions. In arithmetic progression, the missing terms can be found when the first term and the common difference is given. But here, the missing term can be found when the first term and the common ratio of this sequence is what? Provided. So here, with the first term and the common ratio, we can then find the what? The missing term. Now, the missing term, let's call it t sub n. The missing term, t sub n, or the nth term that is missing, can be found by using the formula a rho raised to power n minus 1. So, this is already an established formula, even from our secondary school knowledge. So, this is a topic meant for undergraduate students of the 100 level in the university. So, you are meant to be familiar with this formula. We want to extend your knowledge a little bit from what you have already known in secondary school to something that is a little bit tougher than what you have actually known. So now, we now proceed. We are still discussing about geometric progressions, as we have said. Now, in our last episode on arithmetic progressions, we observed that it is possible to insert arithmetic means in between two numbers. And when we carry out that operation of inserting arithmetic means in between two numbers, we simply form a sequence of numbers in arithmetic progression. But in the same way, it is also possible for us to insert what we call geometric means in between two numbers. But this operation of inserting geometric means in between two numbers will lead us, or will yield a sequence in what? In geometric progression. The difference is clear. I repeat, when you insert arithmetic means in between two numbers, it will yield a sequence of numbers in arithmetic progression. But when you insert geometric means in between two numbers, it will yield a sequence of numbers in in geometric progression. But what is actually geometric mean? I told you we have so many types of means. For example, if I'm given the number 2 and 4, these are two numbers, and somebody asks you to find the arithmetic mean of these numbers. The arithmetic mean of, okay, let me use something like 4 and 8. Okay, 2 and 4 is okay. 2 and 4 is okay? Okay. Okay, it's all right. 2, 4, it's okay. Okay, let's use 2 and 4. Now, if 2 and 4 is given to you as two numbers, and somebody asks you to find the arithmetic mean, the arithmetic mean of these two numbers will simply is defined as what? As the sum of the numbers divided by the numbers. How many numbers you have here is 2. That is 1, 2. Number of times. So 2 plus this gives us 6, and this is over 2, which equals to what? 3. So the arithmetic mean of these two numbers is what? Is 3. In the same vein, if you are now asked to find the geometric mean, mean, GM, general manager. If you're asked to find the geometric mean of two numbers, the geometric mean of two numbers is given by the formula as the square root of what? Of 2 times what? 2 times 4, which will just give us something like square root of what? Of 8, which you can evaluate to get whatever value that it would yield. So you can see that there is a big difference between arithmetic means and what? And geometric means. Arithmetic means and what? Geometric means. Now, if I'm given two numbers and I insert arithmetic means in between them, it will yield a sequence. This operation I have carried out will simply yield a sequence of numbers in arithmetic progression. But if I'm given two numbers and I insert what? I insert geometric means in between these two numbers, this operation I have carried out will what? Will yield a sequence of numbers in what? In geometric progression. For instance, let us look at this. If I have a number like, let's say I have this number, yes, 2. 2 and what? And 2 and 8. 2 and 8. Okay? 2 and what? And 8. This is just what? Two numbers. Alright? Now, it is possible to find the geometric mean of these two numbers. The geometric mean of these numbers, Gn, will be equals, like I gave you, square root of what? 2 times 8, isn't it? And that will simply give us square root of what? 16. And that's equals to what? That's equals to 4. Are you getting the stuff? Now, this is the geometric mean of 2 and what? And 8. Now, when I insert, if I insert this geometric mean in between 2 and 8, that is, I put this geometric mean 4 in between 2 and 8, this operation I have carried out will yield a sequence. You can see it has yielded a sequence. It will yield a sequence in what? In geometric what? Progression. That means what I'm simply claiming is that this sequence 2, 4, 8 is in what? Is in geometric what? Geometric what? Progression. It's in geometric progression. Can we confirm that this sequence is in geometric progression? Yes. We can confirm that this sequence is in geometric progression because you can see that between the consecutive terms, let's say this is the first term, second term, and third term. Now, is there any common ratio in this sequence? Can we find a common ratio between the consecutive terms of this sequence? Yes. Because look at this, the first term and the second term. The ratio between this and this is what? Is 2. Between the second term and the third term, the ratio between 8 and 4 is what? Is still 2. So you can now say that what? That this sequence is actually in what? In geometric what? Progression. And what yielded this sequence? What yielded this geometric progression was what? Was the insertion. The insertion of what? Of a geometric mean. The insertion of a geometric mean in between 2 and what? And 8. So in other words, in conclusion, what we are saying is that whenever you insert geometric means in between two numbers, the operation you have carried out will simply yield a sequence of numbers in geometric what? Progression. And another name for geometric progression is what? Is exponential what? Sequences. Exponential what? Sequences. Now the next question we ask ourselves is that if you are given two numbers, is it possible, because what we have just done here is that we are given two numbers, 2 and 8, and we were able to insert one arithmetic mean in between these two numbers so as to form a sequence in what? In geometric progression. But when the next question we now ask ourselves is that if you are given two numbers, can I insert more than one geometric means? Can I insert more than one geometric mean in between these numbers so as to form a sequence in geometric progression? The answer is what? Is yes. Because when you look at the number, let's look at this, the sequence. If you look at the sequence 2, 4, 8, 16, 32, and the rest of them, you can see that now I am giving this number. This is 2 and what? And 32. 2 and what? 32. You observe first that this sequence, look at this sequence. This sequence is in geometric what? In geometric progression. This sequence is in geometric what? Progression. Are you getting the stuff? This sequence is in what? Geometric what? Progression. And given that this sequence is, okay, but let me not go to this length anyway. Let me take this. Let's say I have the number like I have 2 and I have 32. These are two numbers. 2 and what? 32. Let us see whether we can insert many arithmetic means in between 2 and what? Or whether we can insert more than one arithmetic, whether we can insert more than one geometric mean in between 2 and what? 32. Now watch, you can see that the geometric, what do you call it? Between 2 and what? And 32. The geometric mean of 2 and 32 will give us what? It will give us square root of what? That is geometric mean of 2 and 32 will give us square root of what? Of 2 times what? 32. Which will give us what? Square root of what? Square root of what? Let me see. This is 60 what? 64. Which is equals to what? Which is equals to 8. Which is equals to 8. So, if the square root of 64 will give us 8, and we can put the 8 in between 2 and what? And 30. Let me see, this is 8. You can put the 8 in between 2 and what? 32. You can put the 8 in between 2 and what? 32. Now, in the same vein, if we consider these two numbers, 2 and 8, 2 and what? And 8, it is also possible for us to insert a geometric mean in between 2 and what? And 38. Now, the geometric mean between 2 and 8 is equals to the square root of what? So, yes, the geometric mean of 2 and 8 will give us square root of 2 times 8, which is equals to square root of 16, which gives us what? 4. So the geometric mean between this and this is what? Is 4. We insert it. Then also, it's also possible for us to insert, okay, so now, in the same way, look at this. In between 8 and what? And 32, we can equally insert what? A geometric mean in between it. Because you can find the geometric mean of 8 and what? 32. So geometric mean of 8 and 32 is equals to the square root of 8 times what? 32. And that gives us, let me check my calculator. Square root of 8 times 32 is equals to 16. This is 16. So you can equally have 16 here. So of course, what we are saying is that we have been able to insert more than one geometric mean in between 2 and what? 32. And we observe that this operation we have carried out yielded a sequence in geometric progression. Yes, this sequence is in what? Geometric what? Progression. Now, in the other way around, if I have a sequence, let me clean up this. In the other way around, if we are given a sequence like this, if I have a sequence 2, 4, 8, 16, and what? 32. We have seen that this is a typical example of a sequence in geometric progression. Now, given this sequence, we can then conclude that what? That the numbers in between the first term and the what? And the last term are geometric means. Now, this is this first term and the last term. If you are given any geometric sequence, the numbers in between the first term and the last term are what? Are geometric what? Mean. So all these numbers are geometric means. So we can call this GM1, this one is GM2, that is GM what? I can say G1, G2, G3. Anyhow, I can say G1, G2, and what? G3. Geometric mean 1, geometric mean 2, geometric mean what? 3. So in conclusion, we are actually saying that if you are given two numbers, it is possible to insert as many geometric means as we wish in between the what? The numbers. And this operation of inserting geometric means in between two numbers leads to the formation of a sequence in what? In geometric what? Progression. So simple. I have to state it here categorically that the only way we can form geometric sequences, the only way we can form what? Geometric what? Sequences is by what? By inserting geometric what? Means in between the numbers. The only way we can form geometric sequences, or the only way we can form a sequence in geometric progression, is by what? Is by inserting geometric means in between two what? Numbers. Once we do this, we simply form a sequence in geometric what? Progression. So now, we now head to solve some problems that relates to this part of this work in our next episode of this lecture. So I hope that you have understood what we are saying. We are simply saying that you can insert geometric means in between two numbers, and this operation of inserting geometric means in between two numbers yields a sequence in geometric what? Progression. Thank you for watching this episode. Tune up to the next episode that will now solve so many questions or so many problems on this particular word.